So I'm Joanna Damasconi from Metas. I started working in Metas about 1.5 years ago. And I will present an overview on quantities, geometries, instruments, and measurement methods. So for the agenda, first I will do a brief introduction. Then I will present the geometry of road surface photometry, the quantities we use, and the laboratory and portable instruments that are used to measure those quantities. So first, when we want to light a road, we have to take into account, obviously, the user. So we can think about cars of different sizes that will be driving at different speed depending on the location. But they can also be bikes or e-bikes, and there are also pedestrians, also with different height and with different visual abilities. And so we want to make sure that everyone can use the road safely. And of course, we also have to take into account the energy consumption of the installation. So if we summarize, we have the three main points. So like the safety, I said, of the users, which depends on the driving speed also, and we want to ensure a good visibility on the road. In the cost, we have the lighting plan, so the installation itself that will cost money. And after the installation is done, we will have the energy consumption. And there's also another thema that is the light pollution, which is becoming more important. And this is especially important for astronomy, fauna and flora, and also for humans. So the geometry of road photometry. So here is an image that represents all the quantities that we want to consider. So when we have a luminaire, usually we know quite well the behavior of this luminaire. So usually it's characterized how it emits light. But then the light will be shined onto the surface, and the observer will look at the point on the surface. And so we consider to characterize this reflection of the light toward the observer, we have to consider the angle to the vertical of the light incoming onto the surface, the angle with the direction of observation, which is beta, and the observer angle, alpha. And until now, it was defined as 1 degree observation for road lighting, which corresponds to a distance of 86 meters with a height of 1.5 meters. So if we look a bit more into this, here on left, you have a picture, an example of different observation angles. So you see 1 degree is very far away. And if we look at what stopping distance we have according to the speed we're driving at. So this is according to the French driving code. It's quite similar to the one we have in Switzerland. And so you have that distance of 86 meters corresponds to about 90 kilometers per hour. So this means it's more interurban driving. And one point to consider is that in Europe, there's always less interurban lighting apart in the tunnel. So one goal of the surface project is to revise those angles. And one possibility would be to use 2.29 degree, which is used for road marking and which corresponds to more of urban driving. And this will be explained also in a presentation, as Paola already showed. There will be a presentation on the subject. So now if we look at the quantities we measure, so we measure the luminance coefficient, which is the ratio between the luminance seen from the observer and the illuminance which is incident on the observed area. And we also use the reduced luminance coefficient, which is linked to the luminance coefficient for practical purpose. And so for, these values must be determined for a set of illumination angles, as I showed before, the angle to the vertical and the angle with the observation. And this is the R table. So this is all the points where the quantities should be measured. So it's 396 points. And the brightness we define as the integral over all the solid angle. And there's also the specularity, which is the ratio between two specific illumination angles, which is at tangent 2, which is about 63 degrees over the perpendicular illumination. And then our table, there are different kinds of representation we can make of this. Here on the left, there's the values as a function of the angles in a surface plot. And here on the right, it's the same table, but represented in an indicatrix projected in 2D. And this is also used, this will be used also in the next presentation. So now if you have a look at the instruments that are used for measuring these quantities, we have two big families of instruments. First, there is the laboratory instrument. And secondly, there are portable instruments. So they are quite different and they are used for different purposes. So the laboratory instruments, they're usually very precise. They measure the full R table, so all the values I presented before. And they can be used as a reference. And usually, because they measure all the data points, they are fully or partially automated. The downside is that they have quite long measurement times. They are large and expensive. And they require the extraction of the sample from the road. And it's difficult to put it back when it's extracted. So it means that the same spot cannot be measured more than the exact same spot cannot be measured more than once. And also the extraction is also costly. So the portable instruments, they are used for in situ measurements. They are compact and light. They have shorter measurement times. And because we can use them in situ, we can have a better representation of the road state. So that means we can measure a lot more different spots on the road. And we can also follow the evolution through the years. The downside is that they have higher uncertainty than laboratory devices. They need to be calibrated with a reference from laboratory devices. And they usually are based on a limited set of illumination angles. So I will first go a bit more into detail of laboratory instruments. So here you have two pictures to give an example. So this is on the left, the one we have at METAS. This is a reference plate that we use for calibration. And to give you an idea of the distances here between the center of the sample and the observer, here, which is the camera, there's 1.4 meters. And here on the right, you can see another example from Sirima. And you can see, compared to the size of the screen, that it's also a large instrument. So here you have the observer. Here in the center, there's the sample, and up the source. So you can have an idea that it fills a whole room. And the critical aspects of those instruments, is that so the R table covers specific solid angles, so the data points need all to be measured. And there are 2 degrees of difference between 2 angles in azimuth, and below 0.25 degree of difference between 2 angles in elevation. So that's a really small difference, which is critical for the illumination angle of the system, and also on the detection angle. So we did a review of the different laboratory instruments that we found in Europe, either through people knowing the laboratory or the group, or through papers. And you can see that there are few of them, and they are quite well spread among Europe, but not every country has one. And if we look a bit at the details of what they do, so as I said, they are often automated. They measure the full R table, so that's why it's important that they are automated. They need to have a small angular acceptance of the source and of the detection, as I mentioned before, because of the critical angles that are very close to each other. And it is also interesting to note that some of them are already capable of achieving other observation angles. So now I have a look at portable instruments. So there are 2 different approaches. So usually the most common is that they use fixed sources, like for Collier-Hood from Cerema. So here there are 27 sources. And another approach is like this portable goniophotometer. And this is the one we have at Metas. And this is with a mobile source. So it's able to measure all the data points. So same with the critical aspects that the instruments have to consider. So some of the same are before, but the solution is different. So as I said, a lot of them have fixed sources. So it means that it will not measure the complete table, but it will measure some important points of the table. And then they will rely on extrapolation or interpolation for the remaining points. A lot of them also relied on reference tables, which is why it is important to have a good database. And this will be the presentation of Valérie after me. And another point is that the observation angle of 1 degree is difficult to achieve because of the road surface. So when you do in situ measurement, you have the road surface, and because it's a portable instrument, you don't want it to become too large. So the 1 degree very grazing angle is difficult to achieve. So that's why it could be also interesting to have other observation angles. So we also did the same review of the different available instruments in Europe. There are also a few of them. The Collier-Hood and the NMF box for the Nordic countries are recent devices, but the other ones are already for quite a while used. So for the different approaches, as I said, most of them have fixed sources. The number of sources depends on the implementation chosen. So it goes from 2 sources to 27 sources. As I said already, because of that, they heavily rely on interpolation, extrapolation, and or database, which shows also the importance of having a good database that is representative of the road. The angular acceptance are larger than with laboratory, mainly because the distances are shorter between the observation and the source. And this is something that can be taken into account into the uncertainty, and it's a geometrical aspect that can be accounted for. And the uncertainty of the devices will be also presented in another presentation later on during fall. And here also, some of them can already do different observation angles. So there were instruments that were developed within the project. So first, there's ColorRoot 2. So it was developed before, but it was evaluated. So the performance was evaluated during the project. And there's a second device that is developed by ProCQ. And it is used to measure the road marking in QD at an observation angle of 2.29 degrees. And the idea was to add a measurement of S1 and then to deduce Q0 from the relation between QD S1 and Q0. And we did some tests last fall that were quite promising. And then they continued the development with a prototype, but due to COVID, they had some delay with the electronics. And now if we compare what we can expect the results between laboratory and portable instruments. So here it was studied done with ColorRoot, and it was a comparison between measurement made with the portable device and with the gonio-photometer of CEREMA. And you can see, so on the left it's Q0, and on the right is S1. And you can see there were one or two samples done with the gonio-photometer in the laboratory, and then there were 4 different sites that were measured with the portable device in a spot close to where the extraction of the sample here was made. And you can see that Q0, there's a really good correlation between the laboratory device results and the ColorRoot results, apart from this, for this one. Otherwise, it's quite good. And this shows the reliability of the device. And for S1, we have stronger variation, but if we take a look at it, you can see that also between here for the A spot, so the first area, you can see that between the 2 samples measured in the laboratory, there are also quite large deviations. And actually, most of the portable device, they implement S1 because it's just the ratio between 2 specific illumination angles. Usually, it's implemented directly, so there's no extrapolation or interpolation. And so it means that there are also quite large variation because it's very dependent on the state of the road at the specific point. And to compare more, there will be also an intercomparison that is ongoing. So the idea was to have 7 reference samples that were 3D printed. And they traveled to different laboratories across Europe, and they were measured with 5 laboratory devices and 4 portable devices. And the results will be also presented in another presentation in December because the travel of the samples was a bit complicated due to COVID, and also the laboratories, some of them were closed during this period of time. But it will come in December.